What if the most important skill in science isn't knowing what question to ask, but rather knowing how to find enough people willing to help you answer it? Science, as most of us are trained to practice it, is usually a solo sport, or a solo sport with you and a graduate student. You design a study, you recruit your sample, you collect your data, and you and your student write your paper. Then you move on. The intellectual currency is the idea. The practical currency is the grant, and the sample size is, well, if we're honest, usually whatever you can afford. That model works well for many things. It works less well when the question you're asking is a population level question. When what you actually need to know how human behavior shapes human health across decades is not one study, but 100 studies. Not one cohort, but a consortium. Not one country, but several. Not a few hundred participants, but tens of thousands, followed for months and years. That kind of science requires something most researchers are never taught and many find genuinely uncomfortable: the willingness to give something away. Your data, your methods, your credit, and I'll be honest with you, your control. It requires, in short, the ability to build something bigger than yourself. In 1985, a British epidemiologist named Geoffrey Rose published a paper arguing that public health had been solving the wrong problem. Medicine was exquisitely good at identifying sick individuals and treating them. What we couldn't see, because the tools weren't built to see it, was the population level question underneath. Not, why does this person get sick, but rather, why does this population have this rate of disease? And the difference between those two questions, Rose argued, was not semantic. It was the difference between treating symptoms and understanding how to make the world healthier. That question required a different kind of evidence. Not case studies, not even randomized controlled trials. It required understanding what entire populations actually do with their bodies across entire lifespans and what happens to them when they do more or less of it. Answering Rose's question with the precision it deserved would take 40 years. The invention of an accelerometer and the kind of collaborative ambition that most scientists dream about, but very few achieve. It took someone like Professor Ulf Ekelund. Professor Ekelund is a professor at the Norwegian School of Sports Sciences in Oslo and one of the most cited physical activity researchers in the world. But he didn't start there. He started with 8 speed skaters at a training camp. That was his first data set. 8 people. A few days, and a simple research question. But the bigger research question that he was passionate about, and the questions he really wanted to answer, didn't have the resources available to study them at scale. What he built from that starting point with 8 Swedish speed skaters was 20 years of relentless collaboration, data sharing, and methodological innovation, and is now one of the most remarkable research consortia in the history of physical activity science. His most recent paper, published in The Lancet in January 2026, draws on device-measured data from more than 140,000 people followed for the better part of a decade across multiple continents. It asks a question Rose would have recognized immediately. Not what happens if the most sedentary people meet the guidelines, but what happens if the entire population distribution shifts just a little, 5 minutes, 10 minutes, across every risk level, across every age. The answer changes not only how we think about physical activity and health, but how we leverage that data to shape public health policy. I'm John McGavick. I'm a researcher at the University of Manitoba, and I've spent over 2 decades studying physical activity in children, building my own small consortia, asking my own population level questions, wondering more than once whether the scale was ever going to be large enough to matter. Now, sitting down with Ulf Ekelund for the Emerging Scholar podcast on UMFM 101.5 felt like the conversation I'd been building towards for my entire career. And this is what it sounds like.
Welcome back, everyone, to the Emerging Scholar podcast. It is my distinct pleasure to have one of the world's leading physical activity epidemiologists with me here today, Professor Ulf Ekelund from Oslo, from the Norwegian Sports Science Institute. Welcome.
Thank you very much.
So I've been following the work that you've been doing for a really long time, and I just wanted to start with maybe the very beginning. So the first author paper that I could find from you was published in 2000 and involved 8 adolescent speed skaters who were attending a boarding school in Sweden. You strapped an accelerometer onto them, maybe the precursor for what is the actigraph? And then like 20 years later, you're working with 1 million people. Can you walk us through that journey? What did you learn from those first 8?
Started small and got bigger by time.
So what inspired that study and what did you learn from that study?
I was teaching at a university in Sweden and realized if you work at the university, you really need to have a PhD exam. Otherwise, nobody's going to listen. So I had the opportunity to be enrolled with the PhD program at the Karolinska Institute in Stockholm, which was quite fortunate, but nevertheless. And during that time, being trained in exercise science, I had some training in biology. In Sweden, at that point in time, exercise physiology was a big topic. I mean, very many world-famous exercise physiologists. I suppose I was more interested in, not really in maximal oxygen consumption and the exercise science part, but more on physical activity and how could we really measure physical activity. So I started doing some smaller research with heart rate monitoring, but I started doing some research on measuring heart rate, trying to use the heart rate signal to estimate energy expenditure. For this particular study, the speed skaters, we measured total energy expenditure by doubly labeled water, measured their heart rate with this type of individual calibrated heart rate method. So we calibrated the relationship between oxygen consumption and heart rate in these skaters and estimated their energy expenditure, both from heart rate and compared it to the doubly labeled water energy expenditure estimates. Accelerometry became a method you could use to measure not energy expenditure, but body movement, or it picks up the acceleration signal of the body. And I did the doubly labeled water study in collaboration with Klaus Westerterp in Maastricht in the Netherlands, who is probably one of the leading doubly labeled water experts in the world. And he also introduced accelerometry to me. So I started doing some work on accelerometry.
How big were those accelerometers that you were putting on those speed skaters?
No, they weren't much bigger than those was today, but they...
Oh, right on.
The difference was how the acceleration signal was measured. I think that the size was very similar to the size of today, but the memory capacity was quite poor, and you couldn't collect the data. You couldn't collect the raw data. You could collect data on probably 10, 20, 30, 40 second epochs. If you wanted to go on a very short epoch length, then you had to reduce the measurement time probably to a day or two.
Right. Yeah. And the finding that I guess surprised me, and it sticks with us today, is it worked really well for running, but you also, they were skaters. So you measured them while they were skating.
And we thought that's going to be the case, but we wanted to show it basically. So, even if you think it shouldn't pick up skating, I think it was important to demonstrate. And there are obviously limitations with accelerometry. Maybe the combination of heart rate and accelerometry is preferable, which I've been working with a little bit as well.
And sometimes it's nice to have that, you might call it a negative control, to show that it's picking up what it's supposed to and it's not picking up something it's not supposed to. It was really nice to read that paper. And then I guess to jump forward to the study where I saw your name for the first time because we were doing work in a similar space was the European Youth Heart Study. So you went from 8 to 4 countries and thousands of children. You studied 9 and 15-year-olds. What was that jump like? And were you the one bringing the accelerometry into that study?
Not really. This was also when I was doing my PhD. I went to my first conference, which was the Pediatric Exercise Science Conference, and it was held in Denmark, so it was quite close to Sweden, where I live. And I had started doing some work with, as I said, with heart rate monitoring, and met with a few guys at that conference who were planning the European Youth Heart Study, and they said, "You're doing work on measurement. Maybe you want to be involved in the European Youth Heart Study and contribute." So I did. Obviously, I was very keen to be part of it, and we were discussing how should we measure physical activity in that study, because we wanted to go with a device, not self-reports, because we can't really trust self-reporting, especially not in children. And we started planning the study and thought about it for quite a while, but these earlier accelerometers came along, and we choose to use the accelerometer potentially because it's more feasible compared to if you're going to use heart rate monitoring. You really need the calibration for each individual. The accelerometer is simple to put on, initialize and download the data. So I did quite a lot of that work with the accelerometers. And I was also fortunate during that time to be involved in the development and the validation of the International Physical Activity Questionnaire. So I did all the downloading, data processing of the accelerometer data for that very early validation study.
Okay.
Yeah, I don't remember. I think it was published in the early 2000s, something like that.
Yeah. And when were you developing the EYHS?
And so we did the European UFO study, which was basically set up to understand both how physically active kids are. At that point in time, we collected quite a lot of data, both on blood markers and height and weight and waist circumference and skin folds, and those things. But we were also interested in understanding the determinants or correlates of physical activity. So we had a pretty broad setup in these countries which were involved in the study.
So the first, I would like to hear more about the determinants of physical activity, because that's not something that I think came out first. I think one of the first discoveries from my point of view was this breakdown of light physical activity, moderate intensity physical activity, and vigorous intensity. You guys published that in The Lancet, and looking at cardiometabolic risk factor clustering. So do you maybe want to walk us through that first, and then we can talk about determinants of physical activity?
Yeah, no, that's one of the key papers from the European UFO study, where we looked at, it was purely cross-sectional data, but we looked at the associations between intensity of physical activity and the clustered cardiometabolic risk, or we combined the metabolic risk factors like blood pressure, fasting insulin, triglycerides, HDL cholesterol, and possibly, if I remember correctly, maybe waist circumferences in one risk score, and demonstrated that those kids who were more active had a better risk score compared to those ones who were less active.
And you could extend that to children in Denmark, Estonia, Norway, and Portugal. A question I've always had is, how did those 4 countries actually get involved in this first large accelerometry study?
Yeah, no, that's a good question. We actually performed the European UFO study without any external funding. These studies were funded by the countries.
Wow.
So we submitted application to the European Union. We didn't get any funding. But the original plan was to involve as many countries as possible. But they had to fund the data collection in each country. We had good colleagues in Estonia and in Portugal. So that was set up, so to say.
Like-minded people with the same passion.
Exactly.
And this was a bit of a foreshadowing maybe for the rest of your career, getting used to harmonizing data collection in 4 different countries, harmonizing methods, pooling data, which we'll talk about later, must have been very challenging, but also maybe inspiring to see that you could actually pull this off.
Yeah, it was really inspiring. And I think it was really novel at that point in time to combine data and having exactly the same protocol across the 4 countries, translated questionnaires into the different languages. We back translated them into English and then translated them again. We had training sessions across the 4 countries. Those who were actually going to do the actual data collection, we engaged quite a lot of master students at the different sites who contributed to the data collection. So, it was a steep learning experience for myself and for all of us. For example, we learned that the accelerometers could drift quite a lot if there was a little bit of moisture in the monitors. The data could be completely off. Okay. So we learned that those earlier versions, you could actually calibrate them, a very, very tiny, small little screwdriver.
Oh, really?
And calibrate them manually,
Oh, that's cool. And your work absolutely inspired the analyses we were running at the same time in terms of breaking it down to light intensity, moderate intensity, and vigorous intensity, trying to replicate what you had found, but then extend it to a Canadian cohort, for example. Maybe, can we just go back a sec? What did you find in terms of the determinants of physical activity? I'm not as familiar with that work.
Really need a prospective study. The European UFO study was originally only cross-sectional, and then some of the countries did follow-up studies. And we have some follow-ups in Norway. But a determinant is really needed, or you really need a prospective study. But we, if I remember correctly, we found the usual suspect. I mean, higher socioeconomic status was associated with higher physical activity in these kids. Having self-reported parental activity was associated with higher activity in the children. Obviously, at least cross-sectionally, lower BMI was associated with higher activity. So it wasn't, it was what you would expect.
Yeah, and I think we found the same thing. Two other findings that we have that are probably similar, I would say in Norway for sure. Self-reported time outside after school was a big one. And then the second one was participation in sport.
And we also observed, at least in Norway and Estonia, substantial seasonal variation.
Oh, yes.
The kids were much more active during the summer compared to winter.
Yeah, same. Us too. And weekends were horrible in Canada in the winter. Their daily physical MVPA dropped by like 50% Saturdays and Sundays.
Yeah. And that's quite interesting because, the data we have now in both children and adolescents and in adults shows a very similar pattern. In youth, activity drops during the weekend. In adults, the adults increase their activity during the weekends when they are free and don't need to go to work and sit down at work.
Well, and for us, that was a really important message that we were giving to policymakers, was that the schools are already doing a lot and they're doing great work and kids are active during school. And even the gender gaps or the sex gaps weren't as prominent during the school hours. But as soon as we went to the weekend, everything dropped, the sex differences grew. And so the message to policymaker was, we got to work after school and on the weekends to see how we can get more kids up to that magical 60 minutes a day.
Yeah, and I think that's an important finding, because if you want to intervene, weekends are definitely a way to intervene, at least in children and adolescents. So,
absolutely, I totally agree. And that gets the parents involved and it gets the community involved. And I think that's really key in terms of the socio-ecological model of how to get kids more active.
Yeah.
Now, if we turn back to the large consortia, I guess after EYHS, you had a vision maybe for this next level, which was ICAD. Do we want to transition to that?
Maybe it was a mutual vision with Chris Reddock, who was also involved in the European Youth Health Study. We presented some results at the American College of Sports Medicine annual conference. We're discussing, because there were quite a few studies with the active graph accelerometer around the world, or not only the European Youth Health Study. And we were thinking, would it be possible to pool all these data? And would it be possible to really harmonize the accelerometer data and combine it with all the other information we have on these kids? Many were a bit pessimistic because people thought that everybody should be very keen to their own data and not share our data. But we managed to set up the ICAD, or the International Children Accelerometer Database, 2007, 8 or something like that. And we got some funding from the UK, from the NIH or something, National Institute of Health Research or something like that. So we could employ a PhD student and a postdoc to start doing the work with what we call the ICAD-1, to pool reanalyze all the accelerometer data, all the individual data we gathered, I think in total in about 18,000 children. And then also combine the physiological biomarker data, anthropometry, and if there were data on self-report like sports participation, smoking, diet, alcohol consumption, all those things.
And we've kind of touched on what an accelerometer is, but I think when you're starting to pool all of this data, it might be important for us to explain to the audience, maybe that does epi but doesn't really know an accelerometer, sort of that raw data. And the advantage here is it's an objective measure that allows us to estimate duration of physical activity and intensity of physical activity. And we'll just leave it at that for now. But maybe just explain like what's coming out of that raw measurement. And then maybe we'll get into what it's like pooling all that information.
Early on, the information coming out, you could set up your predefined epoch length, whether you wanted to collect data, as I said, in 5-second epochs or 10 seconds, but to really measure physical activity for a week, which was our aim in the European Youth Health Study, in many other studies, at least from the beginning, and due to the memory size, you needed to have a 60-second epoch. And what you get is simply numerical value, which is called a count from the manufacturer.
Yep.
And it's different between different brands.
Yep.
But that count can then be, as you say, translated into time spent in different intensity levels based on laboratory-based or semi-laboratory-based studies looking at the relationship between these count values and, for example, energy expenditure.
Right. So if a child's going for a run or if they're at soccer practice and they're wearing this device, they're going to get a lot of counts in a minute.
Yeah.
If they're sitting down at school at their desk doing work, they're going to get next to no counts a minute. I was a bit of a fidgety kid. I might have a couple of counts in a minute. So they know that I'm not sleeping, but it's definitely not.
And
go ahead.
Anecdotically, there was one child in the European Youth Art Study from one of the countries, I don't remember which one, who had an enormous amount of physical activity. I mean, it was insane, and it looked nice. It looked perfectly fine.
Yeah.
But there were some periods during the day when he was extremely active, and so they went back to this guy and this kid, and he said, "Yeah, well, I actually placed it on my dog, and we were playing."
You know what?
So it has been used in animal research as well, not only in this case, but in animal research.
Oh man, every time I presented that data, that was the first question they asked. How do you know the kids are not putting it on their dog? And I said, what is the likelihood? But I guess there was one kid. There's one out there. So the epoch length is important because one of the essential aspects of this is you needed 7 days of data. Right? Capturing 1 day of data or 2 days of data doesn't really reflect, and even 7 days, you could argue, doesn't really reflect the seasonal changes or things that are going on in a child's life. But 60-second epochs allows you the memory length to be able to collect the 7 days of data. Every cohort, all these fragmented cohorts across the world, we're collecting them for different reasons. So some people maybe had 15-second epochs, others had 30, others had 60. Some people wore it for 4 days. Some people wore it for 14 days. So when that raw data is coming in, what was that like for you and Chris to try to make decisions around how are we going to pool all this data so that it's something we could use?
And you can always, if you collect the data with a 15-second epoch, you can always interpolate it to a 60-second epoch, because that's simply just summing 4 15-second epochs. Some studies suggested that at least 4 days is needed in children to have an intra-class correlation of, I think it was 0.75 or 0.8, something like that. I think it's a little bit different depending on your research question as well. If you are only interested in, let's say, in a surveillance study, if you're interested in population levels of physical activity and how many people are meeting the WHO recommendation for physical activity, it might be okay to include everybody with just a single valid day.
So just to summarize, if you're interested in a descriptive question about subpopulations and how active they are or how they're not, or maybe changes in activity over time in a population, 1 day of data is maybe enough to make those comparisons.
Yeah,
however, if you're interested in physical activity as an exposure variable, as either something that predicts or causes cardiometabolic risk, you want a much more reliable, much more valid estimate of that daily physical activity dose. Okay, so thinking about the ICAD and movement into this space, in my opinion, and I'm biased because I was studying in this space and working in this space at the same time, this was one of the first individual level meta-analysis done in pediatrics, where studies from multiple cohorts from all over the world were coming together, agreeing that they could pool data and analyzing it as a uniform and saying, here's the power of the sample size and the power of maybe the diversity of all these samples. Would you agree that it was one of the first attempts to make that happen?
Yeah, I think it was. And obviously it required quite a bit of admin work as well. We needed data sharing agreements and all these things. But yeah, when you have the data, when you have analyzed data and drafted some papers, you really forget about those.
Yeah, when the light at the tunnel is just a pinhole, but you know that if you can get through that, It's going to be brilliant on the other side. Our audience is mostly trainees, so we don't want to worry about the darkness of the administrative side of it. If you can get through it, there's gold there. So maybe just tell us some of the early findings about ICAD, because I think that forecasted the next few studies in your career.
It did indeed. And we published a paper in JAMA I think in 2012.
Yep.
Where we looked at, again, it was a cross-sectional analysis, but we looked at the combined associations between physical activity or moderate and vigorous physical activity and sedentary time with the cardiometabolic risk markers. We found was that if you were active, if you belonged to the highest tertile of moderate and vigorous physical activity, you had a much better metabolic profile compared to the other tertiles, regardless of your sedentary time. So, I mean, we concluded that sedentary time probably didn't influence the cardiometabolic risk profile if you were physically active.
Oh, and this drives me crazy. But the term that came across my desk that I saw all the time, and I'm so glad you published this paper, was that sedentary time is the next smoking.
Yeah, sitting is the next smoking. When I give talks about this, I still put up those media headlines. That was one. That was actually one, I think, in New York Times.
Yeah.
Sitting is killing you, even if you're exercising vigorously or something like that.
Yeah. It is true that it's not great, but the appetite for catching on to the next thing is so strong that we lose sight of the main message. And then you replicated it later in 2016 in adults, which maybe we'll talk about.
I mean, it was cross-sectional, so there are limitations. And we are actually right now working on a prospective meta-analysis with individual participant data in children and adolescents with two of my colleagues, where we are using the ICAD database, but also did a systematic literature review to find other studies with the same sort of information, same sort of data, and looking at the prospective association between physical activity and sedentary time with these cardiometabolic risk markers. And I hope we are in the process of submitting that paper, so I hope it's going to be published later.
In preparation for this interview, you published something yesterday in the British Journal of Sport Medicine, I think with Ayman Lee.
Yeah.
So it was hard for me to catch up. But maybe this is a good point to actually talk about, as exciting as this is, there are some scientific constraints to this approach. So you talked about the early work was cross-sectional, but what are some of the things that you can and can't do, or what are some of the inferences you cannot make when you're pooling this individual participant data? And the thing that I think about the most is that all of these studies were designed for different purposes. And so that's very different than the European Youth Heart Study, where it might have been one of the main exposures. And in our work with the Healthy Heart Study, it was the main thing. And so that's very different in terms of a study design feature. So with all these different study design features, what are some of the drawbacks when you're trying to pool all that data?
I mean, one of the limitations is obviously that the harmonizing the acceleration data, as we discussed, we needed to do, say, 60-second epochs. Ideally, you would have a shorter epoch time because that provides you with a higher resolution of the data. More information is always good if you're working with data. It's always difficult to harmonize other variables measured slightly different, measured by completely different persons. And you may measure skin folds in one way, in one country, and slightly different in another country. You have different laboratories to analyze your blood samples, etc. There's always that limitations. Having said that, you try to adjust for cohort or adjust for study in the analysis, but there are limitations. And I think especially when you're harmonizing, let's say, a variable like socioeconomic position. How do you define socioeconomic position? Do you define it as education, which many do in many cohort studies? Mm-hmm. You ask for the highest education. Mm-hmm. But highest education might not be equal to highest income, and socioeconomic position is determined by many other factors, not only your income or your education. So, and then you need to boil it down. So you may end up with 3 categories for socioeconomic position. Some cohorts may have asked do you smoke, yes or no? Other cohorts may have pack years of smoking, which is much more detailed. And then you have to go down to the least common denominator, yes or no, which you lose information.
And that's just the nature of the beast.
You need to upfront say, how have you harmonized the data? And you have to discuss that as a limitation in your study. I do think the size of these harmonized approaches are, if you really want to understand, let's say, dose response associations between physical activity and health outcome, you really need a pretty large sample size. And then if you want to do some stratified analysis or sub-analysis in different age groups or men and women and stuff like that, I think the size is quite key. You get rid of all information biases associated with self-report.
Mm-hmm. Unfortunately, it doesn't pick up cycling, and we get a lot of comments about, what about the kids who are riding their bikes all the time?
Yeah, no, that is true, especially not if you place the monitor on. We did some analysis in a Norwegian data set. We do a national survey with Veterinary Norway, and we also ask questions about those ones who regularly cycle to and from work and for pleasure and for exercise. And when we looked at that, it was a very small proportion. And when we then compared their activity levels from the accelerometer to the others, those ones who reported they regularly used their bike for commuting and exercise, cyclists were more active if we had been able to measure it. It wasn't a very large proportion of the population who actually regularly used their bike. So, but that's one limitation. Mm-hmm. There are others as well. We discussed skating earlier on.
Yeah, skating is another one, which we have a little study on skating that we can talk about later. But the only group, I guess, that would be very active on the bike and then not active at all would be cyclists in the pro peloton who train for 6 hours a day and then sit the rest of the time. So before we get into the paper that you published in January this year, which I thought just really advanced, I think, the policy implications and our understanding of physical activity and health, there were some papers early on, one in 2016 in The Lancet, another in 2019 in BMJ. And the Lancet paper, I think, emerged from that ICAT analysis where you tried to determine whether or not moderate to vigorous physical activity could attenuate or eliminate the effects of sedentary time. And in this case, you went from a sample size of 8 in Sweden to a sample size of 1 million in The Lancet.
We did a Lancet series on physical activity in 2012, which was published ahead of the Olympics in London in 2012. We repeated that one in 2016. And when we were planning the series in 2016, there was, as I alluded to previously, there was a pretty large interest in sedentary behaviors and sedentary time in the research community. Mm-hmm. And some people, there were papers coming out claiming that sedentary time increases your risk for death and cardiovascular disease, etc., independent of physical activity. Mm-hmm. And that was also where the headlines came. Even if you exercise, if you sit too much, you will die prematurely. Mm-hmm. And I was a little bit skeptical to those studies. And basically what they did was that they run the analysis on sedentary time or sitting time or TV viewing time and, let's say, risk for mortality, and statistically adjusted for physical activity in the model. Mm-hmm. Everybody are basically equal for physical activity. But that's not really, in real life, you vary both in your sedentary behavior, your sitting time, and in your physical activity. Mm-hmm. And so we were planning initially for that 2016 paper was that we should do a systematic review and see what's out there. And then ahead of that, or when we were planning it, there was a large systematic review coming out. So we said, we can't do another one. That won't fly with the Lancet. They won't take it. And then we thought, okay, how are we going to do this? We knew there were papers or published papers, cohort data with both physical activity and sitting time, presenting the data. So we did a systematic review. I think we found 16 papers, self-reported data, all of them. And we contacted the original authors from these 16 cohort studies and asked them whether they wanted to contribute to this harmonized meta-analysis. And I was really surprised. I think 13 of the 16 cohorts contributed with data. So we set up a protocol. So we had a harmonized protocol. We asked them to reanalyze the data and send the summary data to us so we can meta-analyze the summary data.
Okay, can I ask a question? Did they know ahead of time that you were trying to disprove the landmark finding that they had made using their data?
We gave them the analysis plan. So we said we're going to look at the joint associations and the stratified associations. So they knew what we were going to, nobody knew the results.
Right.
But that was what we were set out to do. But basically what we found in that paper was that those ones in the highest quartile for moderate and vigorous physical activity had no increased risk of all-cause mortality, nor CVD mortality or cancer mortality, even if they sat for more than 8 hours per day.
Yes.
So we combined 4 groups of sitting time with 4 groups of physical activity into 16 mutually exclusive groups, and then looked at the associations with all-cause mortality. So I think we actually were pretty bold in the conclusion, but we said that moderate and vigorous physical activity, equivalent to about 60 to 70 minutes per day, eliminate the association between sitting time and risk for mortality, which was a bit controversial when we published it. But I think many have changed their mind about the danger of sitting too much if you are physically active.
Yeah, and if I recall, I think we'll summarize this in a minute, but the methodological innovation that was made was to stratify based on your level of MVPA. So if you're, like you said, if you're in the highest level of MVPA, it doesn't really matter if you're sitting 8 hours a day. If you're in the lowest level of physical activity, however, it does matter. And in individuals who are only getting 20 minutes of MVPA, if they are sitting for 8 hours a day, there is an additional risk. So a bit of a moderating effect.
True. Yeah, correct. And the critics of that paper said that, okay, but nobody is active 60 to 70 minutes of moderate intensity. Well, I said, this is what they have reported. And it was actually 250,000 individuals who actually reported that amount of physical activity. I know self-report people overestimate, people probably report more activity. But the fact is that 1/4 of those 1 million people actually reported that amount of activity. So even if the absolute time might not be correct, I think the associations are very much there.
And I think the other important advance here, or decision that your group made, was to not do the meta-analysis of published work, because if everyone had just adjusted for MVPA, you would have come up with the same result.
And that's why we wanted to do this, joint, because it's a different question. Because you can combine physical activity and sitting time differently across the day. And people do that. So it's more like, I think it's maybe reflecting real life a little bit more than just statistically adjusting for physical activity, those models,
And then the transition from ICAD to this paper that we're going to talk about next was the outcome of interest, which was now mortality. So we're moving from cardiometabolic risk factors in teenagers and continuous measures of things that predict hard outcomes, but now we have the hardest outcome. And we're showing sitting is not smoking.
That's true.
And as an athlete yourself in this space, and you know the physiological changes that happen when you're active and the physiological, let's say, de-adaptation that happens when you're sitting on the couch, those two things are wildly different. And to think that sitting could outweigh going for a run during the day, I could not make sense of it. I did not believe any of those headlines.
No, I fully agree. When I finished my PhD, as I said, I did some heart rate monitoring and learned to know Nick Wareham in Cambridge. And he was also doing heart rate monitoring with this flex heart rate method. and asked me whether I would like to come and join him for a postdoc in Cambridge. And so I was supposed to be there for a year. It ended up being 9 years. And during that time, I mean, that's where I learned all my epidemiology. Being in an epidemiology unit at the university in Cambridge was just such an enormous learning experience. It was ridiculous. But we also had that in common, that we wanted to measure physical activity precisely in cohort studies. So that was probably the stepping stone in from the children's studies into these more large-scale studies I've been doing in adults.
What was it about either Nick or about that culture in that institute that kept you there that was really exciting?
Well, as I said, I was supposed to be there for a year. I had my family back in Sweden.
Oh.
I commuted every second week back and forth, and they were supposed to join me, but our kids at that time, they had their friends, they had their sports. They didn't want to move to Cambridge, and my wife was a bit reluctant. So and after the first year, Nick got the opportunity, because he got quite a lot of funding from the Medical Research Council, to set up a unit. And he asked me whether I wanted to stay and lead a research program in physical activity epidemiology.
Wow.
And yeah, I did. I suppose it wasn't supposed to be for 9 years, but that's where it ended up. But it's quite interesting, because when I started in that group, we were about 12, 13 people in the group, in the research group. And when I left, it was about 200 people employed in the unit.
Wow.
So it was just an exponential increase in the output in science and people working. And it was, as I said, it was an enormous learning experience for me.
Awesome. Did your family move to Cambridge after a while, or did?
No, I continued commuting.
Wow.
And I still have the same family, so I'm happy with that.
They had faith.
Yeah, I think so.
So maybe we could move to this wonderful paper that started the invitation for this podcast here, that was published in The Lancet in 2026. And the arc, I think we've seen this passion for the epidemiology of physical activity, for understanding at a high residual level, what is it about physical activity and the intensity or the different levels of physical activity that are important for health in populations. What was the question that drove this new paper in 2026?
I think it was, as I mentioned earlier, the first Lancet series on physical activity in 2012. Lee published a landmark paper in that series on the population attributable fraction, which is basically a measure. So if you remove a risk factor from the population, how many deaths could be averted if you remove that risk factor? So she calculated that if everybody globally who did not meet the physical activity recommendations of 150 minutes of moderate intensity per week, if they were made to meet the recommended levels, how many deaths could potentially be averted? And the figure was about 8 or 9%, meaning that a substantial amount of deaths globally could potentially be averted by being physically active according to the recommendation, meaning if everybody became active. But that is a little bit of a crude measure. First of all, I mean, you treat individuals, let's say, who do 140 minutes to get over the bar of 150 minutes, equal to those ones who do 2 or 3 minutes to get over that bar. And that's a pretty big leap, going from, let's say, 5 minutes per week to 150 minutes per week, compared to going from 145 to 150. But they're treated equally because you dichotomize the data. The other thing is that we know, both from self-report data and from data with devices, that the dose response curve is, I mean, it's curvilinear. You have a really great payoff effect if you go from very little activity and increases a little bit. But if you're highly active, there's not much advantage of increasing your activity even more. So that's non-linear dose response association. The first idea came about in 2018 or something like that, but I didn't know how to analyze it. And then discussed it with my colleagues, and one of our statisticians in Norway. And he came up together with one of my very clever colleagues with this measure, which is called the potential impact fraction, which takes into account the non-linear dose-response association between physical activity and mortality, and can look at very small changes in physical activity. So we had already in 2017 set up this adult accelerometer consortium, which more or less was based on what has been done in children. I contacted colleagues around the world I knew had accelerometer data and mortality data or register data on mortality. I asked them if they were keen to come together to set up a consortium. And as he said, we published our first paper in BMJ in 2019, where we looked at the dose response associations between sedentary time, light, moderate, and vigorous intensity, and risk for mortality. And then we followed up with a few other papers. And now in 2026, we managed to pull this one off on more or less the same cohorts. We also analyzed the UK Biobank data in this most recent Lancet paper.
And so just to summarize, you've done two things that I think are critical from a policy standpoint and from an epidemiological standpoint. The first one from a policy standpoint goes back to the Iman Lee paper, and the population attributable fraction is very, very challenging for a policymaker to even fathom, which is, let's take the whole population and make them physically active enough to be healthy. And like you said, it's also unrealistic to think someone who's just below the guideline has a very easy chance to get over the 150 minutes a week. But someone who is wildly below that, it's going to take far more public health dollars and effort and resources to bring them up to that 150. So from a policymaker standpoint, that's challenging. What if we nudge the entire population just a little bit further towards that guideline? 5 minutes at a time, 10 minutes at a time. And now people can maybe see that. And I want to tie this back to the series that was recently published in Nature Medicine, which you were part of, which leverages healthy cities as a potential way for us to nudge people to that 5 or 10 minutes. So I think that's the first really important distinction that I don't think anyone's made in physical activity epidemiology up to this point, which is, what is the potential impact of just these small nudges, which I think was landmark and really important for policymakers to understand. And that ties into the second real important advancement, which is Jeffrey Rose's landmark paper in 2001. So before we get into the results, could you maybe talk a little bit about Jeffrey Rose? Because it is an anchor for this paper and it's an anchor for the analysis. Could you talk a little bit about what that is and why that was important here?
Yeah, if I remember correctly, his first paper was on sick populations.
Yes.
In National Journal of Epidemiology in 1985. He discussed a population-based approach compared to a high-risk approach, and whether you should aim to shift the entire population a little bit, let's say by lowering their blood pressure, or whether you should focus on those ones with hypertension and try to intervene heavily on those ones and to lower their blood pressure. And what's the impact on population health? I think that was basically what he discussed in that paper. And that, exactly as you said, we were inspired by his reasoning, and we wanted to both analyze small changes in the entire population, or accept the 20% most active, because I don't think we need to bother about those ones who are really active. So we looked at the changes in 80% of the population, and then we had this, what we call the high-risk approach, where we looked at the small changes, let's say 5 minutes increase in moderate and vigorous physical activity in the 20% least active.
Beautiful. And I love the theoretical underpinnings being translated into a practical, meaningful, actionable result in the paper. So do you want to just walk us through what you actually found? If we say, let's take the 5 minutes a day that the journalists were talking about, from the population approach, you saw that for an extra 5 minutes a day of MVPA, 10% of deaths were averted.
And then if we only looked at the 20% least active, we could potentially have 6% of the total number of deaths. Basically meaning that the 60% of the population are not in the lowest 20%, not those ones who are in the highest 20%, in the middle. If they increase by 5 minutes, that's about 4%, 10% minus 6%. So it seems to be more bang for the buck if you increase in the least active, which is what the dose response curve tells us. On the other hand, if we think about it from a public health perspective, it's probably more difficult to intervene in that group and get them more active.
And it's very difficult to get them up to 150 minutes a day. The message being, if you can get 5 minutes per day or 10 extra minutes per day of MVPA, there are meaningful benefits to that movement. And realistically, and I think this is an important observation, is that it gets saturated when you get to people who meet the guidelines. So for individuals that are 30 minutes above, the extra 5 minutes doesn't have the same impact. But for that large number of people that are below those guidelines, just a tiny shift, not saying you have to get to 150. You just have to move yourself toward.
And then I think for individuals, I mean, if you don't do anything, start small and try to gradually build it up to the, let's say, 20 minutes per day, whatever it is. And then you are close to the 150 minutes a week, which is the guideline.
Now, you also looked at sitting time or sedentary time. What was the finding there?
The finding was that if you reduce sitting time by 30 minutes, because we looked at 30 minutes, because I think the average sitting time was about 8-9 hours. So we thought about 30 minutes, that's half an hour. Reducing sitting time by 30 minutes would theoretically prevent 3% of all deaths in this high-risk approach, looking at the 20%.
So again, small shifts. In large populations, leading to benefits, which basically validated the Jeffrey Rose theoretical approach from 1985 and then later revisited in 2001. So in this paper and in some of your other papers, can you talk maybe about some of the major impacts that these papers have had, not only in just our understanding of epidemiology, but some of the practical outcomes that have come from either the Lancet series, this paper, your 2016 paper in the Lancet?
Yeah, the Lancet paper for 2016 has some influence on both the US guidelines from 2018 and the WHO guidelines from 2020, because that was the first time sedentary time was included in the guidelines. So they said both the US guidelines and the WHO guidelines said that try to limit sedentary time, and if you have to sit a lot, try to be physically active at the higher end. And I know that study influenced the guidelines quite a lot because there was a stronger focus on physical activity compared to sedentary time. That sedentary time or sitting time could be harmful, but could also be circumvented by being physically active. So I think that's one of the key findings. We'll see, because I think the Americans are currently updating their guidelines. So we'll see if this paper is going to get some influence. And I think the 150-minute guideline fits quite nicely with what we see in studies with accelerometer data. We saw that in the BMJ paper, in more or less the same cohorts as in this latest paper, we saw that the maximal risk reduction was obtained at about 23-24 minutes of moderate intensity per day. That's slightly more than 150 minutes. I think it's about 170 minutes. So it's very close to the lower limit of the guidelines. And that's probably where we want to aim the population to be active at.
Yeah, and I think it essentially validates the current guidelines.
Yeah.
And then it gives policymakers something to lean into. And I think the follow-up, that series in Nature Health and in Nature Medicine, talking about the challenges we currently face and the role of cities and the role of physical activity promotion and climate change advocacy, combining to shift populations to that 5 minutes or to reducing sitting time by 30 minutes. I think those are all coming together now into a shift in how we interpret this and then how we employ policies to achieve these goals? Something we have not talked about, and I'm going to argue that your work has potentially been instrumental in the reason why we have Apple Watches, the reason why we have Garmin's, the reason why we have Fitbits, even maybe Strava as an extension of that, is that people care a lot about how much activity they're getting or how much sitting they're doing. And that has come from your work.
No, I'm not sure about that. Still, okay.
That's very kind of you. But the large body of work that has informed this is in our consciousness now. And I think this epidemiology really does resonate, especially when journalists pick it up. And we should have mentioned this earlier. The reason we had accelerometers, and we still need them because they're objective, very good scientific tools to measure physical activity, is because we didn't have these tools. Like, we didn't have any of these things. And so thinking back to 2012 or 2016, people were not on a regular basis monitoring their activity with their watch or with their phone. But now, hundreds of millions of people are wearing devices continuously. So this revolution in the accessible wearable data is being leveraged by many scientists. What do you see as the strengths and maybe the drawbacks of incorporating some of this data into our physical activity epidemiology?
Yeah, that's a really good question. I think definitely the strength is the size. There has been some papers on, I think the people who have access to the Apple data, and that's done some really interesting analysis on, wasn't the latest paper on whether physical activity changed when people moved from urban areas to rural areas or the other way around. And there was, I think, one paper on data from Apple Watches during the COVID pandemic and how activity changed. And so I think that the size and is obviously one thing. If there are any limitations, I suppose one of the limitations is that even if many people are using smartwatches, I think it's a selected group in the population as a whole. I don't think we can really get a true picture of the levels of physical activity in a population by using commercial wearables. And I'm involved in WHO's work on surveillance, and they are planning to start using some sort of a device for measuring physical activity in populations, not only self-report, but replace the self-report by devices. And we have had discussions about trying to get access to commercial wearables, but it's probably too selective part of the population who really uses wearables. They are health conscious, they are keen about knowing about their activity, they're probably exercising quite a lot more than the general population.
And they can afford a $300 watch.
Exactly, yeah. And it's probably difficult to do that in Malawi or in Tanzania or in wherever you're interested in measuring physical activity. Yeah.
Exactly. And many of us are blessed with the ability and the resources to have our phones connected and to be able to connect our watch to our phone and our phone connected to a satellite and integrating all this, where in many parts of the world, you do not have that. However, the All of Us cohort in the US is starting to leverage this. And I see a dichotomy in this design in that they want a more diverse representative sample, but at the same time, they're measuring physical activity with devices. And so I'm not sure, as you said, whether or not any of the physical activity information coming from that will achieve the diversity goal. But how do you feel about data? Because All of Us is starting to publish data on physical activity and different health outcomes. They're leveraging UK Biobank as well, which has objective measures and trying to go to.
The other advantage with All of Us is obviously that they have continuous data for years, and whether that outweighs the limitations with potentially a non-representative sample, it might do. And I think it also depends on the research question. I mean, are we interested in associations between data we can get from the device and health outcomes? I would assume that the variability in the exposure is the important thing. And I think you will get that variability even if it's a selected sample. Whether it's generalizable to other populations, that might be a tricky question. Mm-hmm. But you could potentially get the shape of the response relationship between your exposure, physical activity, and the health outcome you're interested in. And if you have, as they have, data for years in these individuals, mm-hmm. you can repeated measures is obviously what we are lacking in physical activity epidemiology with devices currently. Mm-hmm. So there are definitely potential, but also limitations. I mean, we have been using the UK Biobank data a bit, and it's obvious that is a very selective sample. Mm-hmm. I mean, in the entire cohort of the UK Biobank is about 500,000 individuals. That's only less than 10% of those ones who were invited to take part in the biobank. So that accelerometer sample is definitely selected. But you still see the dose response association between the physical activity data and health outcomes.
Mm-hmm. Yeah. And it doesn't always have to translate to the entire population.
No.
And a lot of these data are from older populations. They're not going to translate to 20-year-olds or 25-year-olds.
No. And then there is something we haven't really touched upon. The wearables, the commercial wearables, and the data from the UK Biobank is wrist-worn placement.
Yes.
But the bulk of evidence from research-graded devices are placed on the hip. Mm-hmm. And there are differences between placements. And it's really difficult to compare data coming from the hip and coming from the wrist. If I got to speculate, I think the next generation of physical activity recommendations, I think they will include a recommendation on steps.
Okay.
And there was a large systematic review and meta-analysis on steps and health outcomes coming out last year in Lancet Public Health, which suggested that the optimal number of steps is around 7,000 to 8,000 steps per day. But that was entirely based on accelerometry data from the hip. We know that steps data from a wrist-worn monitor is probably 2,000, 3,000, 4,000 steps higher mm-hmm. than the hip monitor. So that's going to make it difficult to provide recommendations.
Yes, we live on a farm just outside of town, and I was driving home the other day on a bumpy road, and my watch told me I met the current step goal for the day, even though I was sitting there, but my wrist was bumping on the steering wheel, and it was counting every step because most people don't appreciate that a wrist-worn device is vastly overestimating physical activity compared to what we would be capturing on a waist-worn device.
Great.
Maybe just to follow up, in this era of AI and machine learning, is it possible that AI will help us with either these wearable devices or with the large pool of accelerometer data that you have to try to understand some latent aspects of physical activity? A paper came out in Nature Medicine last week looking at, in a specific population of people with heart failure, that you can pick up incidents of disease using these wearable devices, that AI is kind of picking up things that our eyes can't see. Where do you see the AI jumping into this field, and how's that going to advance our understanding of physical activity and health?
I think for accelerometry, I mean, we have 3 signals in the 3 different planes, mm-hmm. and we have a raw acceleration signal, which is possible to measure nowadays with the more modern accelerometers. I think machine learning, which is one sort of AI, definitely can help to translate the acceleration signal into different movement patterns and types of activities. I think the key limitation so far is that we don't have very good annotated data sets. I mean, you really need a very good annotated data set, and physical activity, I mean, free living physical activity, it's a really extremely complex behavior. Mm-hmm. And you will get a complex signal from a wrist-worn monitor, but you need to have data on, let's say, photography on people doing, or preferably a rolling video mounted on the body of the individual.
Yes.
And then someone needs to annotate that data. Okay, now that person is sitting, now it's standing, now it's walking slowly, etc., etc. And then relate that to the acceleration signal to really learn from it.
To train the model.
Yeah, to train the model.
That brings me up to another funny set of questions we got from the youth in the Healthy Hearts cohort we were studying. The older kids, when we asked them to wear the device, they asked us if it had a GPS signal on it because they were worried their parents would know where they were going on the weekends and the evenings. And maybe just to close, things have advanced a great deal from studying speed skaters in Sweden to 1 million people and really reshaping our understanding of physical activity and health. As a grad student coming in now, thinking about where they would want to start their projects, what are some recommendations you're giving to grad students, residents, others entering this field that are exciting opportunities for them to get involved with, or some really important questions that they should be thinking about as they're starting their own career as an emerging scholar?
I think the most important thing is that they should study something they're really interested in. You need to be passionate about what you're doing, especially if you're going to go into a PhD program. You need to be passionate. Mm-hmm. I do think we are probably only in the beginning of understanding the acceleration signal and the combination of, X, Y, and Z signals from monitors and how that can translate into activity patterns. And we could potentially learn quite a lot from exploring that further and understand not only the intensity of activity and how that relates to health outcomes, but also how different types of activities relate to health outcomes. Now we only have self-reported data. So I think that would be one important thing. We also briefly discussed determinants of physical activity, and I'm quite puzzled that we don't know much, even if people have tried to identify genetic markers for physical activity. There are very few so far identified genetic markers for physical activity, and they explain probably not more than 1 or 2% of the variability in physical activity. Mm-hmm. It's really puzzling me because I would assume there are quite strong biological drivers of physical activity and our movement. And I think the concept of not only genetics, but metabolomics and how different proteins are expressed and stuff like that, and that if that could be combined to try to understand physical activity and why some people are inherently active and others are not. Mm-hmm. And finally, I suppose the $10,000 question is, how do we really motivate people to be active?
Yes.
And it's probably different, or it is different between different individuals, but we do have a society where many people sit too much and have too little physical activity. How do we reshape our society, our built environment, etc., to make it more activity friendly? Mm-hmm. There's some big questions, but
those are good. Anyone who's dived into Mendelian randomization, people have tried to create a genetic risk score for physical activity, and it is very poor, but it's also very correlated with weight and obesity.
Yeah.
And so it's a challenge. And that is interesting. If we went to if we had 2 epidemiology conferences side by side in Chicago, and we had all the physical activity, if we had ACSM conference in one conference hall, and then we had just a standard epidemiology conference in the other, you would think that there would be genetic differences. This one group of physical activity scientists, we love physical activity. It is ingrained in who we are. And you would think it's genetic, but maybe it's social. Something drove us into this space. I would say it's deeply embedded in who I see myself as, and I would attribute it to my genes in some way, but maybe it's just the way I grew up. And I would have to say that you're in Norway and I'm in Winnipeg, and I would say the challenges we face are maybe a little bit different. There is something social and structural happening in Scandinavian countries generally, I think, that is changing the way people look at physical activity, and we need to learn from that a great deal.
No, I think you're right. But we are also concerned about people not being active enough. So
It's not the golden goose in the Scandinavian countries either. There are still some public health challenges, let's say.
Oh, indeed.
I can't thank you enough for this and look forward to seeing what is coming up next through this amazing work that you do.
Thank you very much. It's my pleasure.
8 skaters. That's where it all started. A training camp, a research question, a scientist at the beginning of his career with almost nothing to work with except large curiosity and a conviction to do science very well. Where it ended up was 140,000 people followed for a decade. The arc from n equals 8 to n equals 140,000 is not just a story about sample size. It's a story about what is possible when you decide early and deliberately that the question is bigger than any single study, any single lab, any single country. That the only way to answer a population level question is to build a population level sample and the infrastructure to study it. And that the price of doing that is learning to share your data, your methods, your authorship, your credit. With many people you may not have met yet in countries you may have never visited, on questions you may have not even considered. Ekelund calls it building consortia. I call it the hardest thing in science that nobody teaches you how to do. In our conversation today, what struck me most was not the statistics or the effect sizes, though they were very impressive. It was the philosophy underneath. The idea that dreaming big is not enough. That you have to dream big and build big. That ambition in the scientific question has to be matched by the ambition in the scientific infrastructure. And that payoff, if you stay the course, is the ability to say something true about entire populations that no single study ever could. The finding that shook us, the 5-minute daily increase in moderate to vigorous physical activity and the 6 to 10% reduction in preventable deaths is a small shift in an entire population that justifies the question that Jeffrey Rose posed 40 years ago about radical change in public health. How do you nudge populations? It might start with just 8 skaters. Every large answer starts somewhere small. Every consortium starts with one person deciding to share their data. Every population insight starts with someone asking whether the question is big enough and then refusing to let the tools or the issues or the drama get in the way of them asking that question. If you're earlier in your career and you're listening to this and you have a question that feels too big for your current resources, that's great. That's the right kind of question you need to be asking. Find your collaborators, harmonize your methods, give things away, build slowly and deliberately towards the scale the question deserves. Dream big, build big, and answer questions that actually matter. Ulf Ekelund's paper, Deaths Potentially Averted by Small Changes in Physical Activity and Sedentary Time, was published in The Lancet in January 2026. All the references that we talked about and all the papers we discussed today and the links to those are available in the show notes down below. I hope you liked this episode as much as we did. If you have questions, comments, ideas for future speakers or future topics, please email us at scholar@umfm.com. We're about to wrap up season 2. Next week, we're going to take a break. We have one more episode to drop. It will be coming in the next few weeks. We look forward to seeing you then. This has been the Emerging Scholar Podcast on UMFM 101.5. I'm John McGavick. Thanks for listening.
The Emerging Scholar Podcast was recorded in the UMFM studios located at the University of Manitoba in Winnipeg, Manitoba, Canada. This is Treaty 1 territory, the original homeland of the Anishinaabe, the Innu, and on the national homeland of the Red River Métis. Manitoba is also homeland to the Anishinaabe, the Dakota Ayote, and the Dene peoples. We acknowledge that our water is sourced from Shoal Lake 40 First Nation. As a settler scientist working in health research, I acknowledge TRC Call to Action number 18, that health inequities between Indigenous and non-Indigenous people are the direct result of colonization. Winnipeg is the center for reconciliation in Canada, and where we are speaking from today is at the crossroads of Canada's history and Canada's future. We are 3 kilometers away from one of the most sacred meeting grounds for Indigenous people on the plains and within Turtle Island. We are also several kilometers away from one of the last residential schools in the province. We are working collectively on reconciliation with youth, elders, and community leaders to heal from the trauma of colonization, past and present, honor the original treaties, and create a Canada that addresses and eliminates the inequities and injustices of the past and present to create a future for Indigenous children to live and thrive. On behalf of the team at the Emerging Scholar Podcast, we want to thank Osani Balkaran for the great production for our opening and closing themes. We also want to thank UMFM 101.5, especially our executive producer, Jared McKediak, for technical assistance and production on this project. We also want to thank all of our guests for the discussion and the insight that they've provided. Once again, thank you for listening. Be sure to subscribe to the Emerging Scholar podcast on Apple Podcasts, Spotify, and umfm.com.